Hello, today we will be studying about passband data transmission. So this is the block diagram of a general digital communication system. So we have a message source. So it is converted. We have an analog to digital converter which converts this into bits. Then source and got a channel encoder. So those details we will study later. We have a modulator uh, that will do a binary digital modulation or some type of digital modulation channel, so there is noise in the channel, and a detector. This is the receiver side, which will have a channel decoder and source decoder. The uses of it that we will study later. Then we have digital to analog converter and a user. So our aim here is to study about the modulator, the modulation part. Okay, so if you are using a modulator, then this transmission is called as passband data transmission. So the basic difference between the baseband pulse transmission that we have studied before and the passband digital passband data transmission is, let us see. So in baseband pulse transmission, a data string represented in the form of discrete PAM signal is transmitted directly over a channel. Okay, so it is the pulses. First, the binary signal is converted to. So you remember BK. BK was the binary symbols, zeros and ones. So it was converted to PAM signals. That is, so in the last lectures, we used a binary PAM. So it had only two amplitudes, plus one and minus one. So we can have a lot of amplitudes practically. So in baseband pulse transmission, so these pulses are transmitted directly over a channel. Now here in digital passband transmission, the incoming data stream is modulated into a carrier. So for simplicity, we will use only sinusoidal carrier. This carrier will have fixed frequency limits. So these frequency limits are imposed by the channel. So the frequency limits depends on the frequency or the spectrum of the channel or the channel bandwidth. Okay. So here we will use a carrier. So some properties of the carrier is varied in accordance with our digital signal. So the channel used for passband data transmission may be a microwave radio link, a satellite channel, or the like. So the rule is like, if you are having a wired communication, you can use baseband data transmission. It is transmitting a pulse directly. And if you are using a wireless channel, that is, there is no direct connection between source and receiver, then you need to use this passband data transmission. So here we will be studying binary digital modulation techniques. That is, we will consider that the input is either zeros or ones, or input is having only two levels, zeros and ones. Then there is also MRI digital modulation schemes, and we will study later. Okay, here we will use only binary digital modulation. So MRI digital modulation means there will be, or each symbol will be represented as a combination of M bits. The details we will study later. So some basics. The modulation process in digital communication corresponds to switching or keying the amplitude, frequency or phase of a sinusoidal carrier according to incoming digital data. So we have already studied the continuous AM, FM or phase modulation before in your fourth semester. So the difference here is that there the message signal was continuous. So message signal had infinite values. So corresponding to this infinite values in the message signal, in AM signal you will have infinite amplitudes, infinite possible amplitudes. In FM signal you can have infinite possible frequencies, and in and for phase modulation you can have infinite possible phases, because the message signal or the input signal was, or the signal at the transmitter was continuous. It had continuous values. The signal changed continuously. So based on that continuous change, our AM, FM and PM, that is amplitude, frequency over the phase of the modulated signal also varied continuously. Okay. But here the case is different. Here we will have only a finite number of input signals. Okay, if it is binary, then you will have only two inputs, 0 over 1. And if in the case of, or if you are using M array modulation, if M is 4, then you can have only 4 different amplitudes or 4 different input values. So therefore, for modulation also you require only finite number of amplitudes, frequencies or phase. So digital modulation is also, since it has only finite number of changes, so it is also called switching or keying of the amplitude, frequency or phase of a sinusoidal carrier. So there will be only finite number of changes. So the modulation process corresponds to switching or keying, or switching the amplitudes to some finite number of values, or switching the frequencies, or switching the phase of a sinusoidal wave according to the incoming digital data. So there are three basic digital modulation techniques. An amplitude shift keying is a special case of AM, frequency shift keying is a special case of FM, and phase shift keying is a special case of phase modulation. So we will use signal space approach that we have studied before to analyze the modulation schemes mathematically, and to do the performance analysis, that is to find the probability of error. So basically this is our system. The modulator produces one of the two distinct signals. So that is, in binary signaling, modulator produces one of the two distinct signals. Then either it is 1 or it is a 0. So this modulator produces one of two distinct signals in response to one bit of source data. Okay. So there are three different types of binary modulation. One is binary PSK, binary FSK, or binary ASK. So these are represented as BPSK, BFSK and BASK. So it is, the idea is like this. So we are using binary modulation. So we are modulating only one bit, a single bit at a time. So a single bit can be either 1 or a 0. So in the case of BPSK, you will have two different phases. One phase for, or you will change, or you will use two different phases of a sinusoidal signal for representing each of the 1 and 0. That is, 1 will have a particular phase and 0 will have another particular phase. So we are changing the phase. So in binary FSK, as the name suggests, we are using two frequencies to represent binary 1 and binary 0. And in binary ASK, you will be changing the amplitudes of a sinusoidal carrier signal, or you will be using two different amplitudes of the sinusoidal carrier signal, one amplitude for 1 and another amplitude for 0. So we'll start with BPSK. So in BPSK, the symbol 1 is represented as, or 1 is modulated to S1 of t is equal to root of 2 EB by TB cos 2 pi FCT, and 0 is represented as S2 of t equal to root of 2 EB by TB cos 2 pi FCT plus pi, that is root of 2 EB by TB, sorry, plus pi is minus, so minus, so this plus pi, cos theta plus pi is minus cos theta, so it is minus root of 2 EB by TB cos 2 pi FCT. So you can see that we will be using a sinusoidal wave and we are changing its phase. The phase is kept the same for 1 and phase is changed by 180 degrees for 0. So you can see the figure here. So for 0 you have a particular phase, so this is 0, this is 1 bit duration. For 0 you have a particular phase, or the angle is 0 degree, and when the bit changes to 1, what we do is we change the phase by 180 degree. So if 180 degree phase means it should start from here, 180 degree phase shift. So earlier cosine wave was starting from here, that was for 0. For 1 there is 180 degree phase shift, so it should start from here and here it ends, then again it is 1, so the same. For 1 it is starting from here and ending here, okay. Then again comes 0, so there is a 180 degree phase shift, or we will use this symbol which starts from, with this sinusoidal which starts from here and ends here. Again it is 1, so there is a 180 degree phase shift, again 2 zeros, so here we will have a 180 degree phase shift, and here we will use the same signal because it is 2 zeros, then again 180 degree phase shift. So this is how BPSK signaling is done. So in BPSK we will use two different phases. The phase of the carrier remains same for 1, and for 0 phase is changed by 180 degrees. Now we will do a mathematical analysis of BPSK. So TB is the bit duration, FC is carrier frequency. So FC is chosen in such a way that NC by FC is carrier frequency is chosen for NC, chosen to be NC by TB for some integer NC. So this is for getting a integer number of cycles within a duration TB. So you will get NC number of cycles in 1 bit duration, NC number of complete cycles. So that is exactly for a symbol representation or symbol representation. Okay. Then here EB is the transmitted signal energy per bit. So you can see that the energy of S1 square of t, if you do this, you will get it as EB and energy of S2 square of t. So if you do this integral 0 to TB S2 square of t, you will get it as EB. So the transmitted signal energy per bit, that is energy of either S1 of t or S2 of t, is EB. So this pair of signals S1 of t and S2 of t differ only in 190 degree phase shift. Now we will do some analysis using signal space concept. So you can see that we can define one basis function here, that is root of 2 by TB cos 2 pi FCT with 0 less than or equal to t less than TB. That is, for this particular duration, define one basis function phi1 of t as root of 2 by TB cos 2 pi FCT. So you can see that this phi1 of t is having unit energy. So in order to make this phi1 of t unit energy, that is why we are multiplying with root of 2 by TB, then cos 2 pi FCT. If you integrate it, if you square it and integrate it between 0 and TB, you will get it as 1. So this is a basis function phi 1 of t. We have already studied about different basis functions before. So this is one basis function. So using this basis function, I can write s1 of t as root of eb into phi 1 of t and s2 of t as minus root eb into phi 1 of t from here. S1 of t and S2 of t. So this is the most important thing. Binary PSK system is characterized by a signal space that is one dimensional. That is, we have only one basis function and two message points. S1 of t is root AB phi 1 of t and S2 of t is minus root AB phi 1 of t. So you can draw this S1 of t, S2 of t in the signal space like this. So in this signal space there is only one basis function, so you have only one axis represented as phi 1 of t. Then S1 of t is the point root EB phi 1 of t, that is S1 of t is the point root EB at the axis defined by phi 1 of t. So you have only one dimension, so it should fall in a line. The signal space is one dimension, so all the points should fall in a line. Now S2 of t is minus root EB phi 1 of t, so this is minus root EB. So this is called as the constellation diagram for a BPSK system. ഇതിനെയാണ് കോൺസ്റ്റലേഷൻ ഡയഗ്രം എന്ന് പറയുന്നത്. കോൺസ്റ്റലേഷൻ ഡയഗ്രം വരയ്ക്കുമ്പോൾ ശ്രദ്ധിക്കേണ്ടത്, നിങ്ങൾ ആദ്യം ബേസിസ് ഫംഗ്ഷൻസ് ഡിഫൈൻ ചെയ്യുക. ഇവിടെ ആകെ ഒരു ബേസിസ് ഫംഗ്ഷനേ ഉള്ളൂ phi 1 of t. അപ്പോൾ ഒരു ബേസ് ഫംഗ്ഷൻ വെച്ചിട്ട് നമ്മൾ ഡിഫൈൻ ചെയ്യുന്ന വെച്ചാൽ ഒരു ലൈനെ ഡിഫൈൻ ചെയ്യാൻ പറ്റുള്ളൂ. യു കാൻ ഡിഫൈൻ എ പ്ലെയിൻ യൂസിങ് വൺ ബേസിസ് ഫംഗ്ഷൻ. So a line is defined phi 1 of t. A line is defined using phi 1 of t. And then we will represent these 2 points S1 of t and S2 of t as the projection of S1 of t on phi 1 of t. So it is root EB, the point root EB, and S2 of t is the point minus root EB. The distance between these 2 points d12 is 2 in the root of EB. So this is the constellation diagram for a BPSK system. Now we will analyze the decision rule of BPSK. So here we will assume that both S1 and S2 are equally likely. So that is P of S1 equal to P of S2 equal to 0.5. So I think you remember, if the two signals are equally likely, then our detection rule is maximum likelihood detection, that is MAP, the maximum a posteriori probability rule, changes to ML rule if the two signals are equally likely. So therefore the detection rule reduces to ML rule, that is maximum likelihood rule. So we have already seen that if the maximum likelihood rule for an AWGN channel is actually minimum distance rule or minimum Euclidean distance rule, and based on that ML rule we can divide the region into two. For binary case we define two different regions, and if the received point falls in region R1, then we can say that it belongs to, or S1 was sent, and if it falls on region R2, then we can say that S2 was sent. So decision rule. So to find this 0, we have to use the Euclidean distance principle. അപ്പോൾ നോർമലി നമ്മൾ ചെയ്യുന്നത് വെച്ചാൽ ഈ രണ്ട് പോയിന്റോട് യോജിപ്പിക്കുക, അതിൻ്റെ പെർപെൻഡിക്കുലർ ബൈസെക്ടർ വരയ്ക്കുക. അപ്പോൾ നാച്ചുറലി ഈ പോയിന്റിൽ വീഴുന്നതല്ല, റീജിയൻ R1 വീഴുന്നതല്ല S1-നായിരിക്കും ഏറ്റവും അടുത്ത്, റീജിയൻ R2 വീഴുന്നതല്ല S2-നായിരിക്കും ഏറ്റവും അടുത്ത്. ഇപ്പം അങ്ങനെയാണ് ഡിസിഷൻ റീജിയൻസ് നമ്മൾ ഡിഫൈൻ ചെയ്യുന്നത്. ഇപ്പോൾ so we have already studied this, defining the decision regions in some previous lecture. So for BPSK case, The distant region was found by joining S1 on S2 and drawing the perpendicular bisector. ആലോചിച്ചാൽ മനസ്സിലാവും, ദാറ്റ് ഈസ് ദ മോസ്റ്റ് ലോജിക്കൽ വൺ. ഇനി R1 വീഴുന്നതെല്ലാം R1 റീജിയൻ R1 ഏറ്റവും അടുത്ത S1 ആണ്, R2 ഏറ്റവും അടുത്ത S2 ആണ്. അപ്പം നമ്മൾ S1 അയച്ചിട്ട് R1 റീജിയണിൽ വരെയാണെങ്കിൽ അത് കറക്റ്റ് ആയിട്ട് ഡീകോഡ് ചെയ്യാം. So assume that we have transmitted S1 and due to noise the position of S1 changes. Now if it falls on region R1, then we can say that we can be sure that it will be decoded correctly to S1, and assume that we have sent S1 but due to noise it falls on the received point falls on region R2, then it will be wrongly decoded as S2 and that results in an error. Now so based on that we can summarize the decision rule. So guess that signal S1 of t or binary 1 was transmitted if the received signal point R falls in region R1. R1 വീഴുകയാണെങ്കിൽ നമ്മളത് ബൈനറി 1 ആണ് അല്ലെങ്കിൽ S1 of t ആണ് അയച്ചതെന്ന് ഡിസൈഡ് ചെയ്യാം. Now binary 0 or S2 of t was transmitted if the received signal falls in region R2. Okay, that is a decision rule. So that's decision rule we get from the maximum likelihood rule or ML rule for an AWGN channel. So for an AWGN channel, this ML rule reduces to the minimum distance rule. Now we will study the probability of error for BPSK. So assume that S1 of t was transmitted and we need to find the probability of error given S1 of t was transmitted. So S1 of t ആണ് നമ്മൾ ഒറിജിനലി ട്രാൻസ്മിറ്റ് ചെയ്തത്, ദാറ്റ് ഈസ് റൂട്ട് EB ആണ് ട്രാൻസ്മിറ്റ് ചെയ്തത്. അത് ഒരു എറർ ആവണമെങ്കിൽ the received point should fall in region 2. So here you can see that this point 0 is the middle point or it is a threshold. So this is a decision boundary, and you have also seen that the noise is Gaussian, so it will have a bell-shaped probability distribution. So the distribution of S1 of t and S2 of t, so the both will be random and they will be also Gaussian with its mean on root EB and minus root EB. So we have already studied this in one of the previous lectures. That is, if a determinate signal is added to an AWGN noise, then the signal point, then the resultant will have mean as the signal point, and its distribution is Gaussian. Distribution is also Gaussian, that is it will be similar to the distribution of AWG. So that Gaussian is drawn here. So you have two Gaussians. So this is P of R given S1. This is the probability of R, that is the received signal given S1 was sent. So probability that R takes the value root EB, that is the highest or that is the mean, and as we move along the tails this probability decreases. Okay, P of R given S1 എന്ന് വെച്ചാൽ നമ്മൾ S1 അയച്ചിട്ട് R കിട്ടാനുള്ള പ്രോബിലിറ്റി. നമുക്കറിയാം S1 എന്ന് പറയുന്നത് ചാനലിൽ കൂടെ കഴിയുമ്പോൾ അതിന് നോയ്സ് വരും. അപ്പോൾ S1 നോർമലി റൂട്ട് EB ആണ് സിഗ്നൽ സ്പേസ് വരുന്ന പോയിന്റ്. പക്ഷെ നോയ്സ് ഉള്ളതാണ് നമ്മൾ റിസീവ് ചെയ്യുന്നത് റൂട്ട് EB തന്നെ ആവണമെന്നില്ല, അത് അങ്ങോട്ടും ഇങ്ങോട്ടും ഒക്കെ മാറും. അപ്പോൾ നമ്മൾ ഡിസിഷൻ റൂൾ എന്ന് പറയുന്നത് നമ്മളിതിൻ്റെ ഒരു ബൗണ്ടറി വരയ്ക്കും സച്ച് ദാറ്റ് ആ ഒരു ബൗണ്ടറി ഈസ് ഇക്വിഡിസ്റ്റൻറ്റ് ടു ബോത്ത് ദ സിഗ്നൽ പോയിൻറ്റ്സ്. റൂട്ട് ഇ ബിക്ക് മൈനസ് റൂട്ട് ഇ ബിക്ക് ഇക്വിഡിസ്റ്റൻ്റ് ആവുകയാണ്. റീജിയൻ 1 വന്നാൽ അത് റൂട്ട് ഇ ബിക്ക് ആയിരിക്കും അടുത്ത്. റീജിയൻ 2 വന്നാൽ മൈനസ് റൂട്ട് ഇ ബിക്ക് ആയിരിക്കും അടുത്ത്. അപ്പോൾ സോ ഹിയർ വി ആർ സ്റ്റഡിയിങ് പ്രോബിലിറ്റി ഓഫ് എറർ ഗിവൺ ദാറ്റ് S1 വാസ് സെൻറ്റ്. ഇപ്പോൾ S1 സെൻഡ് ചെയ്തിട്ട് എറർ ഇല്ലാതെ വരണമെന്നുണ്ടെങ്കിൽ അത് ഈ ഒരു റീജിയനിൽ 0 റീജിയനിൽ കിടന്നാലേ നമ്മൾ S1 ആയിട്ട് തന്നെ ഡീകോഡ് ചെയ്യും. Otherwise it will be decoded as S2. So probability of error given S1 is probability that R less than 0. 0 is a threshold. Probability that R less than 0 given S1. So it is, so R less than 0 means you need to integrate. So you know that this is having a distribution similar to Gaussian or this is having a Gaussian distribution or the distribution similar to an AWGN, additive white Gaussian noise, but the only thing is the mean is shifted to the signal point. So അത് നമ്മൾ നേരത്തെ തന്നെ പഠിച്ചാണ്. അപ്പോൾ ഇതിൽ എറർ വരണമെന്നുണ്ടെങ്കിൽ it is given that S1 was sent. Probability of error if S1 was sent is actually probability that R is less than 0 given S1. So this is a Gaussian function with mean root EB, and for R less than 0 you have to integrate from minus infinity to 0. അപ്പോൾ ഈ കർവ് എന്ന് പറഞ്ഞാൽ മൈനസ് ഇൻഫിനിറ്റി വരെ പോകും. മൈനസ് ഇൻഫിനിറ്റി ടു 0 വരെ ഇൻ്റഗ്രേറ്റ്, ഈ പോയിന്റ് ഇൻ്റഗ്രേറ്റ് അല്ലെങ്കിൽ ഈ കർവിൻ്റെ കീഴിലുള്ള ഏരിയ ഇൻ്റഗ്രേറ്റ് ചെയ്താൽ പ്രോബിലിറ്റി കിട്ടും. So this curve is having a Gaussian distribution with mean root EB. So probability of error given S1 is you integrate fx of x given x1 from minus infinity to 0. This minus infinity to 0 corresponds to probability that R is less than 0. So you can write this as q of root 2 EB by n naught, and you can see that this is symmetric. So probability of error given S2, that is actually S2 was sent. What is the probability that it will be decoded as S1? So for it to be decoded as S1, it should fall in this region, that is R greater than 0. So probability of error given S2 is probability that R is greater than 0 given S2. So by symmetry it will also have the same value q of root 2 EB by n naught. Q, where q is the q function which represents the tail of a Gaussian randomity. So they have marked P of E given S1 and P of E given S2. ഇപ്പോൾ 0ക്ക് ലെസ് ആണ് R വീഴുന്നതെങ്കിൽ അത് എററാണ്. അപ്പോൾ അതിൻ്റെ പ്രോബിലിറ്റി അങ്ങനെ വീഴാനുള്ള പ്രോബിലിറ്റി P of E given S1, ഇങ്ങനെ വീഴാനുള്ള പ്രോബിലിറ്റി P of E given S2. Now you have two signals S1 of t and S2 of t which are equally likely. Then the average probability of error is probability of S1 of t into probability of E given S1 plus probability of S2 of t into probability of E given S2. So since all the input probabilities are equally likely, so you'll get probability of error as q of root 2 EB by n naught. So, and another important observation is that the probability of error depends on the ratio EB by n naught. EB by n naught is actually energy per bit, energy by signal by noise, or it is something called SNR, EB by n naught. Or more correctly, this ratio is called bit energy to noise density ratio, or SNR per bit. Now we will study the BPSK transmitter. So you have seen this, that this BPSK produces two sine waves, one for 0 and one for 1. Both sine waves are shifted by 180 degree. Okay, so shifting by 180 degree for a cosine wave it changes the sign. So it is cos theta plus phi is minus cos theta. So this is the block diagram of BPSK transmitter. You have an input binary data. So you have a spectrum shaping filter. I assume that we use our normal rectangular pulse. So then you will have the message signal, the input to the modulator. So I hope you remember this signal should have energy root TB and minus root TB. So we make or we generate a pulse having amplitudes plus root TB and minus root TB. Then we will multiply it with a carrier wave. Phi 1 of t is root of 2 by TB cos 2 pi f ct. So phi 1 of t into root TB will be root of 2 EB by 2B cos 2 pi f ct. And phi 1 of t into minus root 2 EB will be minus root of 2 EB by TB cos 2 pi f ct. So these two signals represent BPSK wave. One signal, one normal signal, and the one which is shifted by 180 degree. So okay. So that is how BPSK is transmitted. And for BPSK receiver, we will use a normal correlation receiver. So you will get the received signal like this. So this is actually what we transmitted was root of 2 EB by TB cos 2 pi f ct plus cos 2 pi f ct, and what we receive is root of 2 EB by TB cos 2 pi f ct plus theta. That is, theta is the carrier phase of offset, so there is a change in theta for change in phase, and n of t is the noise. Then for detection, what we use is we will use our correlation receiver that we have studied in second or third lecture. So we will use a correlation receiver. So in a correlation receiver, we will multiply with the basis function and then we will take the integral. So that is what is done directly. I will multiply with the phi 1 of t, that is root of 2 by TB cos 2 pi f ct plus theta, and I will integrate. Then we will have a detector or decision device. It will have a threshold. Then if threshold is exceeded, you will say it as 1, and if the received one is less than threshold, we will map it as 0. So here the threshold we used was 1. So you can remember that. If it is root TB and minus root TB, then the threshold is 0. Okay. If it is greater, if R is greater than 0, then it is 1, and if R is less than 0, then it will be decoded as 0. So here we are dealing only with coherent receiver. So, and we assume that there is phase synchronization. That is, this theta change that we can manage because there is synchronization in phase as well as time. Now we will study the second type of modulation, that is binary FSK. So binary FSK is somewhat similar to BPSK, and the only difference is that here we will be using two frequencies, or we will be keying, or we will be shifting the frequencies. So in binary FSK, one is synthesis 1 of t, it is root of 2 EB by TB goes to pi f1t, where f1 and f2 are the two chosen frequencies, and 0 is represented as S2 of t, root of 2 EB by TB goes to pi f2t. So you can see for 0 you have one frequency, for 1 you have a different frequency, for 1 you have a different frequency, for 0 you have another different frequency. So this frequency is f1 and this frequency is f2. So there is no phase change and there is no change in amplitudes for 0 and 1. So EB is the transmitted signal energy per bit. So interval 0 to TB, S1 square of t equal to that is energy per bit is EB. Then the frequency separation delta F is F1 minus F2. Now delta F, this separation is selected in such a way that S1 of t and S2 of t are orthogonal. So since we are using some basis functions, there is a requirement that the basis function should be orthogonal. That is integral 0 to tb S1 of 2 into S2 of t dt equal to 0. അപ്പോൾ നമ്മൾ രണ്ട് ഫ്രീക്വൻസീസ് F1 F2 സെലക്ട് ചെയ്യും in such a way that this S1 of t and S2 of t are orthogonal to each other. So if we are looking for mathematical correctness, then phi 1 of t, that is root EB into, sorry, I can define phi 1 of t as root of 2 by tb equals 2 by f1t, and phi 2 of t as root of 2 by tb equals 2 by f2t, where phi 1 of t and phi 2 of t are the basis functions, and S1 of t is root EB into phi 1 of t, and S2 of t is root EB into phi 2 of t. So I need to select phi 1 of t and phi 2 of t as orthogonal, or the inner product between 0 to tb S1 of t and S2 of t, sorry, phi 1 of t and phi 2 of t dt will be 0. So here we are using directly S1 of t and S2 of t, since S1 of t is root EB into phi 1 of t, and S2 of t is root EB into phi 2 of t. They are linearly related. Now define two basis functions. Phi 1 of t is root of 2 by tb equals 2 by f1t, or S1 of t is root EB into phi 1 of t. Now phi 2 of t is root of 2 by tb equals 2 by f2t. S2 of t is root EB into phi 2 of t. Now the signal space representation, you will have 2 points, 2 axes represented as using phi 1 of t and phi 2 of t. Now S1 of t is root EB phi 1 of t plus 0 into phi 2 of t. So that is the point root EB 0. S2 of t is 0. Similarly S1 is root EB 0, and the point S2 is 0 root EB. So this is the constellation diagram for a BFSK signal. Then the only most important thing is choose F1 and F2 such that phi 1 of t and phi 2 of t are orthogonal. Then only we can write and draw like this, 90 degrees. Now to find the decision region, here we will use ML rule. So ML rule is actually minimum distance rule for an AWGN. So for minimum distance rule, the idea is join these 2 points and draw the perpendicular bisector. So that will be the decision boundary. 2 regions R1 and R2. All the points in R1 will be closer to point S1 or root EB, and all the regions R2 will be closer to point S2 or 0 root EB. Now assume that we have received an observation vector R equal to R1 R2. So first find where R1 and R2 are the projections of R of t on phi 1 of t and phi 2 of t. So you will get R1 and R2. Now the decision rule is the receiver decides in favor of S1 if the observation vector R falls in region R1. So this decision boundary വരച്ചെങ്ങനെയാണെന്ന് വെച്ചാൽ ഇത് രണ്ടും കൂടെ ജോയിൻ ചെയ്ത് പെർപെൻഡിക്കുലർ ബൈസെക്ടർ വരച്ചു. അപ്പോൾ R1 എന്ന റീജിയണിൽ വീഴുന്നതെല്ലാം S1 എന്ന പോയിന്റിലേക്ക് മാപ്പ് ചെയ്യും, R2 എന്ന റീജിയണിൽ വീഴുന്നതെല്ലാം S2ലേക്ക് മാപ്പ് ചെയ്യും. ഓക്കെ, അപ്പോൾ ഈ റീജിയണിൻ്റെ ഈ ഭാഗത്തുള്ളതിൻ്റെ എല്ലാം മിനിമം ഡിസ്റ്റൻസ് ഉള്ളത് ഈ പോയിന്റ് ആയിരിക്കും, ഈ ഭാഗത്തുള്ളതിനെല്ലാം മിനിമം ഡിസ്റ്റൻസ് ഈ പോയിന്റ് ആയിരിക്കും. അപ്പോൾ നമ്മൾ സെപ്പറേറ്റ് ഡിസ്റ്റൻസ് കണ്ടുപിടിച്ച് നോക്കേണ്ട കാര്യമില്ല, വി ക്യാൻ ഡീകോഡ് ഡയറക്റ്റ്ലി. So if R1 is greater than R2, then the receiver decides in favor of S1. That is, if the observation vector R falls in region R1. Now we will study the expression for probability of error. So given that S1 is transmitted, then R1 equal to root EB plus N1 and R2 equal to N2. So if S1 is transmitted, then R1 is root EB plus N1. So S1 is root EB and R2 is actually 0. So it is 0 plus N2. R2 is N2. So if R1 is less than R2, so this decision region is actually R1 equal to R2, this decision boundary. So if R1 is less than R2, the receiver will make a decision in favor of symbol S2. So you can observe here. If R1 is less than R2, R1 ആണ് ചെറുത്, R1 എവിടെയൊക്കെ വരും, R2 വലുതാണ്. അപ്പോൾ ഈ രണ്ടാമത്തെ റീജിയനിൽ വീഴും. സോ ദിസ് ലൈൻ ഈസ് ആക്ച്വലി R1 ഈക്വൽ ടു R2. ഈ രണ്ടാമത്തെ റീജിയനിൽ വന്നാൽ ഓട്ടോമാറ്റിക്കലി പോയിന്റ് S2ലേക്ക് നമ്മൾ മാപ്പ് ചെയ്യും. ഓക്കെ. Now the probability of error. The probability of error happens. You assume that symbol S1 was transmitted. The probability of error happens when R1 is less than R2 and S1 is transmitted. S1 ട്രാൻസ്മിറ്റ് ചെയ്തു, പക്ഷെ R1 ലെസ് ദാൻ R2 എന്ന റീജിയനിലേക്ക് പോയി വീഴും. അങ്ങനെ വരുമ്പോൾ പ്രോബിലിറ്റി ഓഫ് എറർ ആണ്. So that is probability of E given S1 is probability of R1 less than R2 given S1. That is probability of root EB plus N1 less than N2. So now define a new random variable N is equal to N1 minus N2. So since N1 and N2 are Gaussian and they are IID, that is identical and independent and identically distributed. So N1 and N2 will also be Gaussian with mean 0 and variance N0 by 2. Sorry, N1 and N2 is given as Gaussian with mean 0 and variance N0 by 2. Then N is also Gaussian with N is N1 minus N2, mean 0 and variance N0. So അത് അങ്ങനെ വരും. അപ്പോൾ ഇതിൻ്റെ വേരിയൻസ് N0 mean 0 ആയിട്ടുള്ള Gaussian ആയിട്ട് വരും N1 minus N2. So P of E given S1 is S1 അയച്ചാൽ R1 ലെസ് ദാൻ R2 എന്ന് പറയുന്ന റീജിയനിലേക്ക് വരികയാണെങ്കിലാണ് എറർ വരുന്നത്. R1 ലെസ് ദാൻ R2 is means root of EB plus N1 less than N2. R1 less than R2 means root of EB plus N1 less than N2. So we define a new random variable N equal to N1 minus N2. N1 and N2 is Gaussian with mean 0, variance N0 by 2. So N is also Gaussian with mean 0 and variance N0. Now that implies probability of E given S1. Probability of error given S1 is P of N less than minus root EB. That is Q of root EB by N naught. So probability of error for BFSK by symmetry, P of E given S2 is probability that R1 greater than R2 given S2. So it is equal to Q of root EB by N naught by symmetry. Same. So since two signals are equally likely, then the average probability of error for coherent BFSK is P is Q of root EB by N naught. So for BPSK it was Q of root 2 EB by N naught. So probability of error for BFSK is 3 dB worse than BPSK. BFSK is having more probability of error. So BFSK transmitted. So here we will use on off signaling. So if so here we can have 0 or 1. So if it is 0, then here it will be 1. So if but here it will be 0. So 0 into this will be 0, but here we will have, since here there is an inverter 1, so if the input is 0, our output will be root of 2 by TB cos 2 pi f2t. Now if the input is 1, then output will be then here the input will be 0. So 0 into root of 2 by TB, you will get it as 0 here, and here the output will be root of 2 by TB cos 2 pi f1t. അപ്പം അങ്ങനെയാണ് ഈ ട്രാൻസ്മിറ്റർ വർക്ക് ചെയ്യുന്നത്. 0 ആണെങ്കിൽ ഇവിടെ 0, ഇവിടെ 1 വരും. അപ്പോൾ ഈ സിമ്പിൾ കിട്ടും. 1 ആണെങ്കിൽ ഇവിടെ 1 താഴെ 0. സോ you will get this signal. So combining it, you will get the binary FSK wave. For 0 you will have frequency F2, and for 1 you will have frequency F1. And for detection we will use the correlation receiver. So you get the received signal, you will multiply with both the basis functions phi1 of t and phi2 of t, and then we will do the integral, or we will do the integration, get R1 and R2. So then if R1 is greater than R2, I will decide in favor of 1, and if R1 is less than R2, I will decide in favor of 0. So that was the decision rule. Now